I'm coming to the MDA 102. So let us continue what we did last week. Just to remind, we were dealing with the local behavior of functions, which was read of the infinitesimal data. So we knew what the derivative was, what were the higher order derivatives, that we had the Taylor expansion with remainders, and now it's time to go further. So what we start with, or what I start with, is the so-called asymptotic estimates. So that means that if you remember, so we had with the Taylor expansion, we had the formula that if I change the position of my argument by the increment v, then I can start with fx plus, then there will be the derivative of f at the point x times v, but that's the linear approximation, and we know that linear forms in dimension 1 are just multiplication by constant. Therefore the derivative looks like a number, and this goes on, and then we have something like a k minus first derivative of the thing at x, and that's multiplied by a v to k, but that's because all the multilinear forms, if it's k-linear form, it must be only a constant multiple times the k's power of v. So there is no other k form on one-dimensional space, plus there is the remainder, and the remainder is the, well, I forgot to write 1 over k minus 1 factorial here, and here will be 1 over k factorial, so the same shape of the remainder as here, except the k's derivative is then taken in x plus t times v times, well, here should be k minus 1, sorry for that, times v to k, and here the t is between 0 and 1, so it's somewhere in the interval between x and x plus v where we have to evaluate the thing, right? And you see here the remainder is in some sense of the order v to k, right? So if I just take the Taylor expansion only up to, so the first k terms starting from 0 ending by k minus first, then I achieve the approximation with error which is of the order v to k, and that's exactly what's meant by the asymptotic estimates, right? So if I have two general expressions, g of h and f of h, so here I have h instead of v, no difference, then I say that asymptotically for h going to 0, the first expression is roughly the same as the other expression if the limit of those two, of the quotient of those two exists. So I go with h to 0 and I compare the value, and if it converges to some finite real a, then I imagine that asymptotically it's of the same order of magnitude, right? So it's just up to a scalar multiple a, it will be the same. So that's how we get the asymptotic estimates. And now, well, I should have also told that there is this big O notation. So we say that G is O of h, f, so f is the lower one. But of course, I mean, we know that if f of h is not of limit 0, then we can also just swap it, and we will have 1 over a there. That's by Audi. So it's reciprocal in some sense. So but G is O of h, O of f it's this way. And you see that in this case the error, so this is the remainder r, and the remainder r of, well, that's r of v, and the remainder r of v is O of h to k. well, not h, but v. Right, so that's the asymptotic meaning of our Taylor expansion. Now if we go here, we can come back to the differential, right? So the differential, if y equals f of x, then we wrote that dy was f dash of times dx. If I rewrite this as df at x at v equals f dash x times v, right, then just what we had here above, this guy says exactly that actually the differential of f is approximating the function in the asymptotic way, so that it gives R the asymptotic estimate of order OH, right? Because you see, if I look here, then I can split it, and you will see that here you just have the f dash times v, so that's cancelled, the v and v up and down, so it remains only a number, and it says that the derivative is just the number, right? So understanding the derivative as a number is saying exactly that the asymptotic estimate is OH, right? So I just wanted to illustrate this at this point, but let's go further. Let's think, what does it mean if I would have, say, something like 0 increment up to all orders? So if it's asymptotically 0 to all orders, can it be that the function itself would not be 0? So this is a very well posed question, and if we go back to our analytic functions, so those written as power series, so that's the case where the Taylor expansion does converge and converges to the function itself, right? So then, of course, if all the derivatives will be 0, which means we have got the asymptotic estimate as being 0 up to all orders, then it means that all the coefficients are 0 and then the function is 0. But clearly, it's easy to see that there are functions which do not have this property. And let's start with the, well, perhaps maybe for data analytics, the most important function at all, and that's this. It's the Gaussian function, right? So you will meet the Gaussian functions everywhere, in physics, in data science, in statistics in general, so everywhere. And the function is just the exponential, but the argument of the exponential with the Euler number e as the base is not just x, but minus x squared. So it means at 0 it will be 1, so we are here. And the bigger x will be in absolute value, the much more bigger will be x squared, so also the exponential e to x squared, and e to minus x squared is just the reciprocal value. So what we have is a function which just is attached to the 0 values very, very firmly as soon as we see x as anything really visible, like here in the picture already with x equals 4 or minus 4, it's undistinguishable on the screen that it's not 0. But we can also write a function f which will be g in the reciprocal value of x. What will happen then? Then if the closer x is to 0, the bigger is 1 over x in absolute value, and therefore the function g of 1 over x will be small beyond any expectation. So, and that's exactly what you see here. So around 0 it looks like the function is just 0, and then it starts growing up, because actually it's well defined for all x not equal to 0, and for all of those x is positive, strictly positive, but very small. So in total what you get is you get a function which has got the infinite behavior, so there will be an asymptote which is exactly at the level of the value of e to 0, which is 1, right? So it's here. So here will be an asymptote there will be an asymptote going this way at the level 1, and the function at 0 will have all derivatives 0, and still it will be always positive, strictly positive outside of 0, and we just to make it continuous, we just add the 0 value in the point 0. So here in the text you can see explicitly how it happens. So you can see that if I draw the function, why doesn't it work here? If I draw the function and its derivatives, so it's nice that the function is so flat. Well, in this scale 1 is pretty low, it's here. But the derivatives start to be wiggling very much around 0, right? So that's what's on the picture. And it's computed here by means of the L'Hopital rule, so it's quite interesting exercise to go through and compute that it's really true and that it makes sense that the derivatives will be there for all orders and there will be always 0. So I will not go into details here, but having this beautiful function e to minus 1 over x squared, we can easily do something like elastic, absolutely smooth jumps. So jumps with functions which will have everywhere derivatives of all orders, but there will be just constant 0 going from infinity up to here, and then being constant, say 1, going from some given value here, and in between it just smoothly goes. So it's a smooth version of the LU function, which you perhaps have seen in machine learning quite a lot. So and it's quite often necessary to be sure for, say, at least theoretical reasons, when you want to show that something works, to have all the derivatives. So that's what we can achieve. Or you see, if alpha, so that's the jump here from this 0 to this 1. Here it's 0.8. In the definition upstairs here it's just 0.4, so it goes very much faster, and this is something which is useful, and to understand it, it's quite easy. So you see, so this is our G1. Well, actually this G is what I previously called F. And now with the G you can just do the functions like this one. So you simply take G, well, A and B is, AB is any interval, and this function will be 0 up to A and 1 starting from B, which is easy to see, right? Right, so that's the smooth functions, and the moral should be that actually, as we already know, there is very little to be written down as expressions in the elementary functions. There is a lot of possibilities. There is a huge space of all the power series which converge on some given interval, but there are still many more functions, and the space of our smooth functions is much bigger than that. So that's the first contribution to this week. I will come back to you soon.